Does anyone here have experience with 3D printing sort of thing? Have you used any of the printers on campus? Taking that as a no, we'll get started. So I want to start off by just giving a brief overview of essentially how 3D printing works, right? The kind of overview from start to finish of creating a model, getting it ready, and how that goes from, an idea to something you can physically print on your device. And we're going to start out by just contrasting it real quick with some traditional manufacturing techniques. So conventional manufacturing is usually one of two types. There are others, but just as an overview, subtractive manufacturing is where you take a large block, right? So some single item, and you successfully cut away from it to get to your fixed size and shape. So this would be, an example would be, say, an aluminum laptop chassis, or wood, really, right? Because you have a tree that is a set size and shape, and then you're cutting that down into whatever you want. But essentially, the idea is you have a thing, and you cut off of it, and by cutting off of it, you get to the object that you want. That contrasts with injection molding, which takes a liquid raw material, usually plastic or sometimes metal, a pre-made cast and removed once it's hard enough to hold its shape. So examples of this would be stuff like phone cases or water bottles, right, where the plastic's melted and then poured into a mold and let to sit and dry and cure, and the end result is what you need. 3D printing works a little bit differently than either of these. 3D printing is what's called additive manufacturing. So the idea with this is that material is deposited onto itself. So you have an initial layer on the print bed of the machine, and then layers, very thin layers, usually some fraction of a millimeter, are slowly built up on top of it to get to whatever you want. So just an overview of a 3D printer. This is a Prusa i3 Mark III's. There are many. Starts with a filament spool. So this is literally just PLA plastic. Oh, PLA is one option. You have others, but PLA is really common because it works well in this use case. But it's just thin plastic in essentially a very long string and put onto a spool. So then the filament from that spool is extruded into this extruder assembly that has a drive gear, which is just a little motor that pushes the filament down, and then a nozzle. The nozzle is heated up to very high temperatures to melt the plastic, and then the melted plastic is extruded out of the tip of the nozzle, right? You can imagine sort of like frosting on a cake, right? It's brought in, melted, and extruded out the tip. Then you have your various drive belts. So screws, belts, really depends on your printer, that sort of thing. But the end result is that provides X, Y, and Z motion for your printer. It's convention that XY is the forward, backward, and left to right motion on the bed, and that Z is the vertical. And then you have your print bed itself. The print bed can be heated, and heating will help with things like making your print stick to the bed a little bit better when it's printing those first initial layers. We'll talk about this more, but it doesn't have to be. All right, so that's an overview of a printer. Next, we're going to take a look at some of your software options for actually making a 3D model. So as you can see on the list, there are quite a few, right? Anything from beginner tools up to multiple hundred of thousands of dollars for professional grade tools. So you really have options when it comes to this. Today we're going to be doing a quick demonstration, and we're going to actually demonstrate using two tools: Autodesk Tinkercad, which is super easy to use and free, and FreeCAD, which is free and open source software. You should have gotten a link via email that explains how to download this stuff if you wanted to follow along. And FreeCAD is a little bit harder to use than Tinkercad, but that also means that's a little bit more capable, right? All right, next, the process of preparing to print itself. So you have a program that's called a slicer. This slicer takes your 3D model. So the 3D model, you can imagine, is like a series of faces. So if you have like a cube, right, it explains where all those vertices are on the cube, each of the corners, and then your computer could read that file and know how to render it on screen. But what a slicer does is it converts that sort of geometric view into very, very thin two-dimensional layers. And that explains to the printer, like, okay, we're going to print out this layer, extrude filament in these areas at this level, and then move up a level and then extrude filament here, and so on and so forth. The slicer that you use is something that's highly dependent on your particular printer, right? You can use any slicer with any printer, but usually for a given environment, it's recommended to use the slicer that is produced by the same people who make your printer. That just makes things a little bit easier. So if you're using a Prusa Mark III's, you'll use PrusaSlicer, which is what I'm going to demonstrate with today. If you're using something like an Ultimaker S5, you're going to use Cura, which is also produced by Ultimaker. Here's some of the 3D printers that are available at UWEC. So in the Blue Gold Makerspace in the library, there are 3 Prusa i3 Mark III's. So the makerspace is pretty much closed this semester due to COVID-19, but if you talk to the right people and email around, it's possible that you can get use of these for some projects. So it's worth mentioning, and they will open up in the future. Also, the computer science department has the JAMF lab, which is in Phillips, near the department offices. They have an Ultimaker S5 as well as a MakerBot Replicator 2X, which is an older printer, but a lot of fun to play around with if you like tinkering and really getting into things. So that's it for the slideshow part of the presentation. Does anyone have questions before we move on? You can feel free to, say it out loud or use the chat. All right. So then if no one has questions, I think I'll just move into the demonstration rather. So as I mentioned, I'm going to demonstrate using first Tinkercad, and we're going to create a relatively basic model in Tinkercad. It's a simple tool, so we're going to create a little model in that, and then we'll move on to into FreeCAD rather, and make a model in there. And for this demonstration, we're actually going to be making a set of drawers, right? It's like a modular set of drawers that you could put on your desk, say, and you could have, say, 2 drawers in it and a casing to house the drawers. So we're going to make the casing first in Tinkercad, and then we're going to make the drawers in FreeCAD. When we're done with that, we'll go over to PrusaSlicer and just demonstrate how to get this ready to actually print if you wanted to do that. At any point, feel free to stop me and ask questions. Yeah, this is here just, as something fun to do and as a resource. So then I will share back on screen. So this is Autodesk Tinkercad. This is also the part if you want to follow along, feel free to do so. So after creating an account on Tinkercad, I'm just going to go and select the Create New Design button. That'll load up the Tinkercad editor, and it'll give it whatever name it feels like giving it. So Tinkercad works on the idea of additive and subtractive objects. So you create an object, you create another object, and then what you get as a result is either the combination of those 2 objects touching each other or the difference of those 2 objects, one removing mass from the other. That'll make more sense in just a second. So we're going to create a rectangular drawer casing, right? So I'm actually going to create it so that the up direction on this work plane here, so like X and Y, the horizontal dimensions are on the plane, and then Z, the vertical, is coming out of the computer screen. And I'm actually going to create the drawers so that it is facing up, right? So that you put the drawers in vertically. And that just makes things a little bit easier to work with in this environment. All right, so we're going to start by creating a box. We'll just click to put that down. And here we can set our length, width, and height of the box. All of these values in this case are in millimeters. So we'll say maybe 150 by 150. And the height, that's how deep we're going to want our drawer. So maybe, well, we could say another 150. Be good just to make a cube. All right, pretty big work environment here, but that does what we need it to do. All right, the next thing I'm going to do is grab this subtractive box, which is this top one on the right here, and we're going to create that item. I'm just going to place it out to the side for now. So this is going to be the mass that we're taking away from our cube, right? So if I were to just export this and print it as is, we just get a massive cube. Not all that interesting. But we need to hollow it out in order to make room for our drawers. So I'm going to create two openings, one on top of the other. So two rectangular openings on here. So the length of these. Length, I believe, is vertical direction. Someone remembers? Okay, yeah. So 150 minus, say we want quarter centimeter thick walls on there. So 25, or yeah. Am I doing that right? 25 millimeter? Yeah. So we're going to have 3 of those total, so minus 75 millimeters. So that's going to put us at, I'm bad at doing math quickly. We'll make it just a ballpark. It'll be fine. Everything's fine. So make one a little bit smaller than the other. Then the width, that's a little bit easier to do, 145. And then the height, we'll also make the back just a little bit thicker to support taking the drawers in and out constantly. But again, it's going to be open on the one side, so we can also do 145. So now we have this sort of open area that we want to put into our box. So if we navigate down, go a little bit closer to our item here, it's a little bit hard to see, but you might tell that there are a couple different grab points on this box. Those grab points help you control movement and essentially working with your model in this space. So if I grab this top one here that looks like a cone, I can move it up. And if I move that up 5 centimeters, now the top face of this box is flush with the top face of the other box. And from there, we can move things just kind of freehand. And we'll move that into place. I'm actually going to put it up kind of toward the back. And you could be very particular about the positioning of everything, but we're just going to get it close for now because this is a demonstration. Cool. Now, what's next? We have a box inside another box. We need to get the difference of these boxes so that we actually get some space in our item. So what I'm going to do is select both boxes. It's just using the keyboard shortcut. In my case, on a Mac, it's the Command key. And that allows me to select multiple things at a time. I believe it's Control on Windows. Next, let's see. Okay, there we go. We have both selected. Then I'm going to select this group icon. It's also Control G. When we do that, you'll notice it's taken the difference of our object. That was the leftover from me pressing the wrong key. But now, our box hollowed out in one area. All right, let's do that one more time. So we still have our big box. Let's create another small box. So width is again going to be our 145 or so. Our length in this case, 90. We can ballpark this. And height, 145. All right, I'm going to do the same thing as we did before. So I'm going to grab this cone shape at the top and move it up by 5 centimeters. So that's flush with the top of this. And then just slide it into our position. All right, we can take a look at that real quick. Yeah, that looks about right. Maybe move it down just a tad. Awesome. We can do the same thing as before then. Select multiple items and hit the group button to cut them apart. Now, as you can see, we have our drawer unit. Does anyone have any questions about that? Any questions? All right, I'm going to move Teams real quick so that I can see it. All right, cool. I'll make things a little bit easier to work with. So now that we have this model, we need to export it into a format that can be read into our slicer later on. So the way we're going to do that is with the export button in the top right. If we select that button, it'll give us some options of what we want to export as. Now, Tinkercad allows you to export directly as a 3D print into some pre-made templates for specific printers. I wouldn't recommend using this personally. Unless you have those particular printers and are using the exact same settings that they're expecting you to, you're not going to quite get the results you want. Plus, it doesn't give you the options to, mess around with some of the stuff we'll look at later in the slicer. So we're going to use the download option and select an STL file. There's another option called an OBJ file. Those are almost the same as STLs. It's a slightly different file format, but it's something along the lines of, say, the difference of a PNG image file and a JPEG image file. There's a little stuff going on, but you can get the same result. So now we have our .stl. So if we take a look at our .stl file real quick that we created, and named it based on what we named it, so you'll rename that real quick. You can see that that is our drawer unit, ready to go. So on macOS, I'm just using the preview provider to view this, that is pressing spacebar. On Windows, I believe the built-in Paint 3D tool can do the same thing, just showing the contents of a 3D model. So this 3D model describes the shape of the item. It has all the vertices between the faces on here, but it has no information about how this model should be printed. We'll get to that in a minute. But first, we're going to create our drawers in Tinkercad, or not in Tinkercad, I'm sorry, in FreeCAD. So let's jump over to FreeCAD. So this is the FreeCAD software and what it looks like when you first open it up. So the first thing I'm going to do is select this Create New button here on the left. So a thing to keep in mind is that Tinkercad is a much more robust, but also hefty software compared to something like Tinkercad. So FreeCAD is going to be much more powerful. It has a lot more features involved. You could theoretically design, an entire engine or something of that, complexity in something like FreeCAD. But that also means that you need to work in the way that it's expecting you to work. So for 3D modeling, it's going to be a little bit slower to use, but again, more powerful tools, easier to do complex tasks. Select Create New. Then I'll go over to Tasks in our combo view on the left. I'm sorry. Need to switch over to Part Design on the top. So where it just says Start, we're in the Start view set here. Move over to Part Design. All right, now we have a task to create a body. A body is FreeCAD's word for a physical item. And you start a body by creating a sketch. A sketch is a 2D item that you then extrude to create your 3D object. So it's sort of like the idea of drawing something in 2 dimensions on paper and then expanding the paper outward to create your item. So you'll draw the face of it in one way, and then you'll make it have thickness. So that'll make more sense in a second if you haven't worked with it before. It's asking us what plane we want to start on. We can just start on XY. There's no real need to be specific on that. And then we have our XY coordinate plane here. All right. So FreeCAD is what's called a constraints-based CAD tool. CAD is computer-aided design. So you create lines and lines and shapes and that sort of thing, and then you combine them in specific ways. I'm not going to pay attention to dimensions very much here, but again, if you're making this for production use, I'd recommend to make sure that everything matches up between your models for obvious reasons. So we're going to start by just creating a line. So I selected the line tool, and we're just going to draw the line. I'm drawing it intentionally crooked to represent that it's not, it's not held down anywhere so far. So if I hit escape to go back to the mouse tool, this line is completely fluid. I can move it around the page. I can expand it and rotate it. Oop, that requires grabbing it. But yeah, I can expand it and rotate it and do all that those sorts of things. There are no constraints on this item. It can float freely. So the way that we create an object that's useful to us is we add constraints. Constraints specify things like the distance between two lines or shapes, and the length of them, and whether or not they're parallel to a surface. So let's do some work to get this line up against our x-axis here. So I'm going to come up here and find the parallel tool. So create a parallel constraint between two lines. All right, so we're going to select our line that we created, and then we're also going to select the axis. And we're going to make them parallel to each other. Now, as you can see, I can still move this around physically, and I can still make it larger, smaller, and move it up or down, but I can't rotate it anymore. A parallel constraint does exactly what you're expecting it to do. Next, I'm going to do a distance constraint. So the horizontal distance between 2 points. So the points I'm going to select, I know this is a little bit small, but the points I'm going to select are the origin and the left side of our line. Now it's asking me for the horizontal length between them, and I just want to be 0. I want that line to be tied to the origin. Now we're going to do the same, but a vertical constraint. So select the vertical distance constraint and attach those to each other. All right, taking a look at our line now. If I grab the other end that we haven't put anything on, I can make it larger or smaller still, but I can't do anything else. It can't go up or down because I have that vertical constraint. I couldn't move the left-hand side of it to the left or right because I had that horizontal constraint, and I can't rotate it because it has a parallel constraint. A good way to keep track of your constraints is where it has solver messages on the left, and that explains what it's found when it's figuring out how to render this after you add a constraint. So it says, under constrained sketch with 1 degree of freedom. Can you guess what that 1 degree of freedom is? It is the horizontal length of this particular line. So let's set the length. So the way that we can do that is, again, with a horizontal constraint. We could set a horizontal constraint between the origin and the right-hand side of the line to whatever length we want it to be. Or we could use this other tool that says fix the length of a line or the distance between a line and a vertex. And that allows us to set the length of this line directly. So if I select that tool and then just click on the line anywhere on it, it'll immediately snap to whatever I want the length of this line to be. Now, you'll remember that I made our drawers 145 millimeters wide. I'm going to make this a little bit less than 145 because 3D printers aren't perfectly accurate. So we'll say maybe 142. This is something that you want to play around with, know your printer, but just a couple extra millimeters is usually a good idea. If you're working with more precise equipment, so a project that I want to talk about a little bit afterwards if we have time, but a personal project of mine is 3D printing a 3D printer. And for something like that, I had to run calibration on my printer to figure out its specific margin of error and then account for that in creating models. Now we have our line. Now notice, fully constrained sketch solved in 0 seconds. There's no way that this can be moved anymore. Now let's add the next 3 lines to finish off this rectangle. So we'll draw a line from there to there, from there to there, and there to there. We now have our lines. I'm going to do this kind of quickly because it's just the same thing again. Create a parallel constraint between this one and this one. All right. Creating a 0 length constraint between the left-hand side of that line and the origin. And setting the length to 142 millimeters. Now, we still have a degree of freedom with this line. You can still move vertically, so we'll set its vertical distance. For vertical, for this one, I want vertical distance between there and there. Okay. We're going to make this for our, what do we do? I can look back at this and see. Do I have a ruler? Well, that's not incredibly useful. Well, we'll just eyeball it for now. We'll say that this one's a 60 millimeter tall drawer. All right, and now for our left and right hand sides, saying the vertical distance between this bottom endpoint and the origin to 0 millimeters, between the top and the top to 0 millimeters, and using a parallel constraint between it and the y-axis, and then saying its horizontal distance between this top point here and the origin. You could also use the bottom point and the origin. It doesn't really care as long as those points line up. Saying that that is 0. Same thing for here. Going to do from this point to this point of 0. From this point, I don't need another horizontal. Yep. Parallel constraint between there and there. Vertical distance constraint from there to there of 0. And still says we have 1 degree of freedom. Oh, yep, the top of this line can still extend. So we'll do vertical constraint from there to there. Now the lines all turn green, marking that we have a fully constrained and filled constraint. That this shape is, a solid surface. Let's take a look at what that means. But first, are there any questions about this sketch tool? All right, moving on. So first thing I'm going to do is hit close on the left-hand side here. And I am going to save our file, because we have not done that yet. So we will say drawer insert. Save that to the desktop. Knew I was tempting fate. I knew that I was tempting fate. All right, this is something that you might notice. When you get to complex CAD software like this, there are specific things that you need to remember to do and not do so that it may or may not crash on you. We've just experienced a small crash. So I'm going to change gears just a little bit in the interest of not wasting our time. I'm going to pull up a model that I created some time ago for a different purpose. Just take me a few seconds to pull up. Not project files. All right. Come on, FreeCAD. Nope. Oh well. All right, there we go. So demonstrating real quick, this is a much more complex drawing, but it has the same fundamentals that I just showed. So I'm going to show you how it works in essentially the same way. All right. So looking at this object, it's a piece for a 3D modeling kit. So you can kind of get an idea of how it looks. So it's all based on sketches, just like everything we've done before. So if I open up this sketch real quick, now it's a much more complex sketch, has many constraints that you can tell, that you can see here, but it's the same idea, right? Drawing lines, in this case, a couple of curves to get a surface that is robust enough for you to work with, right? So getting a object that is closed is really the big idea. I showed with the drawer that we needed all four sides to connect there, and that's just making it a single plane with defined edges that can then be worked with in a more complex way that I'll show in a second. So then we create extrusions on the sketch. And the extrusions, the goal of them is to add depth to our item. So once we have the sketch, which is a two-dimensional object, we can extrude it outward and inward. So in this case, I extruded it outward to make it thick, to make it physically, thick in some way. And then we can extrude back inward to remove mass from it. So there's really no set direction to how you need to set up an object like this, right? In terms of whether you want to create a sketch that is a very perfect model of exactly what your item needs to look like, and then just extrude that out. Extrude mean adding that thickness. Or if you want to make a rough appearance of what you want your thing to be, extrude that out, and then create sketches on top of it and extrude those back in. And those sketches that you extrude back in then could remove mass from the object that you created. Sorry that we had technical difficulty, but does anyone have questions about this? And I can share more resources if anyone's interested. Any questions? All right. Okay, so the final thing that I'm going to show is PrusaSlicer. So this is the slicer program created by Prusa Technology that is essentially made for their printers. So again, as I mentioned, you can use almost any slicer for almost any printer, but there's a lot of details that need to be considered when you're setting up something to go from this conceptual idea, right? This combination of faces in three-dimensional space that make up your object. So let's close out of FreeCAD for now. So something like an STL file, right, that has faces and it has thickness and all that kind of stuff, but that is still relatively simple. Take a look at our drawer. And getting this into a condition that it is printable. So let's take a look. When you open PrusaSlicer for the first time, you're going to get something called the configuration assistant. So that's just going to ask you essentially what printers you have, that sort of thing. I'm going to be setting this up for the Prusa i3 Mark III's with a 0.4 millimeter nozzle. The reason that I'm doing this is because these are the printers that the Blue Gold Makerspace in the library has. So, again, use whatever you have available. But if you want to use the Makerspace, which has extremely low cost, use of their 3D printers, limited by COVID constraints, but all the same available, this is a good place to start. So once you run through the configuration assistant, it'll dump you into essentially this view, which is a picture of the bed of the printer. So if we actually jump back for a second to the PowerPoint, you can see the physical bed of the printer here, right? And the shape of this and the text on it too, they copied over, is the same as what we see in PrusaSlicer. And that's just a helpful tool to give us an idea of how physically big this item is. So if you're wondering, this is 250 millimeters by 200 millimeters. So you can measure that out. So like 2.5 decimeters by 2 decimeters gives a rough idea of how big the print bed is. What we'll do is we'll select the add button in the upper left, and that'll allow us to import the STL file that we created into our slicer. If I just select open on that, we have our drawer unit. There we go. And our drawer unit actually came in really well, but for the sake of demonstration, I'm going to rotate it ever so slightly. All right. So I'll give you a better idea of what these tools do in just a second, but we'll say that the drawer came in like this. Right, so this is looking at the printer. It would print starting at the bottom and going up to the top. Next, let's take a look at the print settings on the right-hand side. There are a bunch of presets, which, frankly, the presets are usually really good. You can do things like mess around with the exact speed of the printer at different points in time, right? How fast it's moving the extruder nozzle across the print and how much filament it's extruding. But honestly, the people who make the printers are pretty good at determining levels that are good enough for most purposes. You can get slightly better performance if you're willing to mess around with it, but a lot of times, at least for Prusa, this 0.2 millimeter quality setting is what I recommend in general. So the first part of it, 0.2 millimeter, that's saying how thick each layer is, each of the vertical layers that's printed. So this will have 0.2 millimeter thick vertical layers, and however many of those are necessary to get to the height of the drawer. And then quality versus speed, those just are descriptors for their presets. Speed is a little bit less time intensive compared to quality, that sort of thing. If I select 0.2 millimeter quality, filament, it's Prusa Mint PLA, which is, again, Prusa PLA. Yeah, that's fine. And the printer we selected earlier. There's an option for supports. Supports, well, we'll get to that in a second. And then infill, which is for the areas that are inside the print. So right, like inside this divider here between the levels, or inside the back or left or right walls of the print. So the area that you think of as full of plastic, what percent full do you actually want that to be? If you made 100%, your print is going to take a really long time. It's going to have to extrude plastic into that entire area at every single one of those 0.2 millimeter thick levels. So you can save a lot of print time and money in terms of filament and, again, printer cost by setting your infill to something less than 100. 15 is the default. Frankly, 15 is pretty darn good. I've gone as low as 5 without any negative effects. Just know that your object will become, lighter weight and a little bit less resistant to crush and damage. Any questions so far? Okay. To get an idea of what this is going to look like, we're going to select the Slice Now button in the bottom right corner. The program is called a slicer. What it does is slicing our 3D model into those layers. Give the slicer a chance to work. Sometimes it takes just a few minutes to actually calculate how this needs to be printed. All right. Now I have this option on the side here that allows me to drag through the print and see it before and after each and every layer. So if we look at the bottom here, so I'm now within the bottom, so this is our entire thing. Actually, I'll do it at the middle. It's a little bit easier to see. I'm inside the middle of the two drawers. Let's zoom into that. So if we zoom into that, you'll notice this really weird pattern. So this pattern here is what's used for the infill. So again, it's only 15% filled in these areas. So actually, let's drop this down a little bit, see if we can make it a little bit easier to see. Yeah, there we go. All right. So instead of using, like triangles or squares or something like that to fill in this gap between the top of our bottom drawer and the bottom of our upper drawer, it's using this wave pattern. This pattern in particular is called gyroid. So that's one of the reasons you can get away with really low infill percentages. is these patterns that it uses are structurally more sound than doing something like triangles or rectangles in your print. And that's just due to the nature of the material you're printing with. So can anyone here guess what's going to be the problem with this print as is? So you set up this to print, and it looks like it's going to take 22 hours and 23 minutes to print. So that's one problem. Printing is time consuming. Large objects, you usually want to cut down into some smaller objects. So like this drawer could be made out of modular segments, that sort of thing. But does anyone have an idea of why this particular item would not successfully print? Feel free to speak up if you have an idea. Anyone?
The panels probably wouldn't hold up very well.
Yeah, exactly. So if you'll notice here for the top of the drawer unit and for this inner layer of the drawer, you're trying to print a lot of plastic, a lot of stuff over nothing. Remember that when the plastic comes out of the extruder nozzle, it's fully melted plastic. So like these vertical walls will be relatively fine because it's printing plastic on top of existing plastic. But when it has to bridge this gap here, that bridging is going to fail. With a good quality 3D printer, something like a Prusa or an Ultimaker, you can bridge a decent distance. You could bridge 1, 2, maybe even 3 centimeters. But I guarantee you're not going to be able to bridge across half the print bed like we have here. So you have a couple options to fix this, right? Because obviously this surface is, if you tried to print it, it's just going to cave in partway through the print, and then you're going to have a mess. So your options are as follows. Now, first thing you can do is this supports option up here in the top right that we skipped before. Supports runs an algorithm to determine what extra structure could be built inside and around your print to support whatever it is you're trying to print. So we'll say we have options for support on build plate only, support enforcers only, or everywhere. Let's try the enforcers only setting. Hit slice on that. That didn't quite work, so we'll try it again. We'll try just the everywhere setting for supports. All right, it made supports. It looks like our drawer is completely filled in, and well, it is, with very, very lightweight support material. So essentially the idea with this is it's going to create something inside these drawers so that it can support the mass of the new surface that's going to print on top. There are downsides to this as well, though. Well, the first of which being you're going to have to tear all this off when you're done. Like you finish your print, okay, now time to spend some time with an X-Acto knife cutting off all the support material that was printed along with it. Let's look at some other solutions because supports aren't really the way to go for this particular print. So we'll set our supports back to none. I'll hit slice now just for a view of it. All right. Now in the bottom left, if I go back from the layer view, which is the multiple layers seen here, to the 3D editor view, which is what we started in where we placed our item, notice these tools on the left. The first one allows us to physically move the item on the print bed. Now, its algorithm, if you run this arrange button at the top here, it will place everything in its optimal position so that there's less space between items. Say we were printing multiple things at once, and we just don't want to take absolutely forever for us to get our print done. We can use the arrange button, and it'll try to move things close together so that there's less time wasted where the nozzle moves between items at a given layer. But if that's not doing what we need to do, the move button allows us to physically move it on our own. Another one is the scale button. That allows us to physically adjust the size of our print. So say we're printing something like, well, a D&D model is a really common thing that the makerspace sees. And for some reason, the person that made the model decided that it needed to be 3 feet tall. Well, it doesn't need to be 3 feet tall. This is how you fix that without, without introducing a lot of work. The next one is the rotate option, which allows you to manually rotate items a little bit. That would be nice if you're working with something that didn't have flat surfaces, say a 3D model of a brain or something, along those lines. That would allow you to get the flattest part of it facing down. The options that we're going to use are place on face and cut. First, I'll demonstrate cut. Cut allows you to set a point where it chops it in half. So one option would be to chop it in half somewhere in the middle of this middle layer here, and then print the bottom as one print and the top as another print. So you can do, I'm just unchecking the box to keep the lower part, and then I can select perform cut, and now we only have the top half. Cut would be one solution for this. Another is place on face. This allows you to select a face of the item, any of the basic 6 faces that it recognizes, to be the down face. So we're actually going to select the back of our drawer unit to be the down face. And now if we take a look at it here, we don't have any of those really long overhangs, any of those really long bridging areas that we had before. Everything just prints on top of existing plastic. Well, perfect. Let's hit slice now. And there we go. A very clean print, very easy print to do. So if I come all the way down here, you'll see it's printing that infill pattern on the inside, and there's not much plastic involved. We can bump this back up to 15. Make our drawer a little bit stronger. All right. As you can see, when I set it to a higher infill density, our pattern here just got much, much smaller and a little bit more complex looking. Go through that. And we have the rest of our drawer built on top of that. All right. And that concludes my 3D printing demonstration. Does anyone have any questions? That's pretty much all I had planned for today. So if anyone has questions about access to 3D printers on campus or ways to get started in 3D modeling, feel free to ask, or you can email me or email the SACM address. We can get those forwarded around.
I don't have any questions, but thank you for doing the presentation.
Yeah, thanks, Brandon. All right, then Aaron, I'll pass the meeting back to you.